Welcome to section 6.3. In this section, we're going to be talking about the concepts of the kernel and the range for a linear transformation. And this is a pretty long section, so we're just going to dive right into this. So we have a linear transformation T going between two vector spaces V and W. The kernel of the transformation, the kernel of T, is going to be the set of all vectors in the input vector space in V, such that those vectors get transformed into the zero vector in W. Okay, so the set of vectors who get transformed into the zero vector in W. This is how we define the kernel of the transformation T. So visually, you can see on my little diagram right here, we've got the vector space V that gets transformed into the vector space W. And you have all the elements in this region right here. All of these, when you transform them, when you run them through T, they produce the zero vector in W. So everything in this set is an element of the kernel of T. So the kernel is all those vectors that get transformed into zero. Of course, this is not necessarily all of V. Right? If all of V got transformed into zero, that's a whole different, very unique case. But it's just any vectors that get transformed into the zero vector in W. So a theorem for us, because kernel is an element of V, it is a subset of V, we can prove that the kernel is not only a subset of V, but that it is a subspace of V. So in order to prove that something is a subspace, we need to show that it is closed under addition and closed under scalar multiplication. So we need to check those axioms, A1 and A2. So for A1, we let V1 and V2 be in the kernel of the transformation. So when we say we let V1 and V2 be in the kernel, what that means is that T of V1 is the zero vector in W, and T of V2 is also. All right, so then we consider T of V1 plus V2, which we know because T is a linear transformation. Remember, we're not proving that it's linear. We're proving that the kernel of T is a subspace. So because this is a linear transformation, we know that it respects addition. So we can split that up. And we know each of these adds up to the zero vector in W, which when added together gives us the zero vector in W. So we showed that given two vectors were in the kernel, so they transformed it to zero, we can see here that the sum of them also transforms into zero, meaning that it is closed under addition. So thus, V1 plus V2 is in the kernel as well. And for A2, to show closure under scalar multiplication, we let V be in the kernel of T, and K be a real number. So we want to show that this is closed under scalar multiplication so that K times V also transforms to zero. So we can go ahead and move the K out because we already know this is a linear transformation. V transforms to the zero vector, and any scalar times the zero vector is the zero vector. So thus, K times V is in the kernel of T. So therefore, since we have closure under addition and closure under scalar multiplication, the kernel of T is a subspace of V. So it is a subspace of the input vector space. That is where all the elements of the kernel are. So let's take a look at an example. So we've got a transformation going from M2 to R via this transformation. So we've seen one like this in a previous section. Find a basis for the kernel of T. So we know that a matrix A, B, C, D is in the kernel of T if and only if that matrix gets transformed to the zero vector. The zero vector in R is just the number 0. So in other words, A plus D has to become 0. Right? If this matrix, whatever it is in the kernel, the result when you transform it has to become 0. So this, we can go ahead and rewrite this a little bit. This means that D has to be the opposite of A in order for this to hold true. Thus, the kernel is going to be the set of matrices A, B, C, negative A. So anything that has this form will be in the kernel of this transformation because it would result in a 0 out of the transformation. So now how do we find a basis for this? Well, we use a method that we've seen in the previous chapters. We can bust out the variables, right? Create a linear combination and then take all of the vectors from that linear combination, right? We know that the linear combination will span all of those vectors, and that provides us with the basis. So then we have, so A, B, C, negative A. That's going to be A times 1, 0, 0, negative 1, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0. So the basis is just going to be the set of the vectors. So 1, 0, 0, negative 1, 0, 1, 0, 0, and 0, 0, 1, 0. So this is an Li set of vectors that span the kernel of T. Okay, so any linear combination of these will produce a vector that's in the kernel, and therefore would get transformed to 0. So this is our basis. And it's just a side note here. It didn't ask about like the dimension, but we can talk about the dimension of the kernel because we have this basis here and it contains 3 vectors. So we know the dimension of that kernel is 3. We'll be talking a little more about the dimension of the kernel and such a little bit later on in the section. Let's take a look at another one. So we've got a transformation from P3 to P2 with the given transformation there. Find a basis for the kernel of T. So the elements of the kernel are going to be coming from the input vector space, okay, so from P3, but transform into 0 in the output vector space P2. So we'll have, so ax cubed plus bx squared plus cx plus d is in the kernel of T if and only if this side becomes 0. So in order for that side to become 0, this term has to be 0, this term has to be 0, and this term has to be 0. So if we look at the coefficients, right, these are the ones that are being dictated by the polynomial on the left. So really, as long as a minus b is 0, b plus 3d is 0, and c is 0, that will be sufficient. So if all of these become 0, when you transform a particular polynomial, then that polynomial is in the kernel, because that's what it means to be in the kernel. Now, what values of A, B, C, and D make this happen? Well, this is where we can start bringing in our understanding of matrices. So we go ahead and set these equations up in a matrix. So we get 1, -1, 0, 0. We get 0, 1, 0, 3, and 0, 0, 1, 0. And all of those equations are equal to 0. You can see here, it's already in row echelon form, just in this current setup here. We do have a free variable, so D is going to be free, so we'll call that T. C is 0, we know that. B plus 3 times T is 0, so that means that B is -3T, and A minus -3T is 0. So that's plus 3T, so subtract that over. We also get -3T for A. So the kernel of T is going to be a set of polynomials from P3 that have this relationship among their coefficients for A, B, C, and D. So it's going to look like -3T times x cubed plus -3T times x squared plus 0 times x plus t So if we simplify that down a little bit, so we get -3tx cubed minus 3tx squared, that's 0, so just plus t. So any polynomial that has this form, okay, for any real number t, will be in the kernel because it will transform into 0 on the right-hand side. So for the basis, again, we bust out the variable. The variable is the parameter t from that free variable. So we pull out the t and just take the vector itself. That's going to be -3x cubed minus 3x squared plus 1. That is our basis. And then any multiple of this, okay, for any real number t, would produce an element of the kernel. But this is the basis for that kernel. And again, note, it didn't ask for the dimension, but we can give it. It only has one term in its basis. So dimension of the kernel is 1. Next up, something a little different. So working with the matrix transformation. The matrix transformation, we saw this in the previous section, going from Rn to Rm. We use an m by n matrix times that input vector x, that solution vector. The kernel of a transformation like this, so this is going to be the set of x vectors in Rn such that t of x equals 0. Right? That's how we define the kernel, right? It's all the vectors that get transformed into the 0 vector. Now, the transformation itself is the matrix transformation, so this will just be A times x equals the 0 vector. So it's the set of all vectors that are the solution to this system of equations, essentially. And this system of equations, because it's equal to 0, this is a homogeneous system of equations. And the solution set to a system like this has a special name that we've talked about in the past. This is the definition of the null space of the matrix A. So it turns out for the matrix transformation, the kernel of that transformation is the null space of the matrix. It's the null space of the matrix of the transformation. All right. So that's the kernel of a transformation. Now we're going to take a look at the range. So the range of a linear transformation T, this is going to be the set of all transformed vectors V such that V is an element of the input vector space. So again, just to be clear, the range is the transformed vectors. So it's not the vectors on the inputs, it's the outputs that we get from the transformation. That's what's in the range. So this is going to be a transformation of this linear combination, which would be the span of this set of transformed vectors, where v1, v2, v3, v4, all the way through vn is a basis for v. So, I have my diagram here for us to take a look at. So what's happening here? Basically, the range of a transformation is going to be the set of vectors that everything in the input vector space transforms to. So everything in here transforms to something in this part of W. This is the range of T. It doesn't necessarily have to transform to all of W. Okay, if it did, that would again be a special case. But there can be values in W that maybe didn't get transformed from V. Maybe V only transforms to a certain type of vector in W. But regardless, the range is going to be the set of all transformed vectors from V. And we typically write it in this form because that makes it a little bit easier for us to visualize. Because I can't literally make every vector V and transform every single one of them. I have to pick and choose, but we know that we can create, using a basis, we can create any vector in V that we want. So if we can transform the vectors in the basis and then span those, that's the same effect as saying we're going to transform every vector in V. Okay. So again, when we're finding the range, we're looking at output vectors from all of the transformed vectors coming in. Okay. So again, we're going to transform all the vectors in a basis for V. And when we transform them all, we'll span that, and that's going to fill that entire range. So let's take a look at what that looks like. So we're going from M2 to P2 using this transformation. What is the range of T? All right. So we're going to span a transformed basis from the input vector space. So these are all 2 by 2 matrices. So we're going to go ahead and take transformation of 1, 0, 0, 0, transformation 0, 1, 0, 0, transformation 0, 0, 1, 0, and transformation 0, 0, 0, 1. So these 4 vectors inside here, those form the basis for M2. We're going to transform all of those and see how much of P2 we cover. So going back and referring back to this. So these 4, so say these, 1, 2, 3, 4. Any linear combination of those 4 gives us all of V. when we transform those four, we're going to see how much of W gets covered by the span of those four transformed. That span, how much we covered, that is the range. Okay, and again, it's not necessarily all of W. It can be, but not necessarily. So we're going to see how much it covers. How many different types of outputs can we get? So if we go ahead and perform the transformation, so we'll start 1, 0, 0, 0. So that means A is 1, B, C, and D are all 0. So that's going to be 3 plus 0 plus 3x squared. For 0, 1, 0, 0, so B is 1, A, C, and D are all 0. So that's 0, 1x plus 1x squared. This one, C is 1, everything else is 0. So that's 1 minus 2x minus x squared. And this one, D is 1, everything else is 0. So that one is just 0. So the span of all of these vectors gives us the entirety of the range. Now, we can make a couple notes here. So like this one, including a 0 in this set of polynomials, that's not very helpful. Like if we were creating a linear combination of this, saying like, like C1, C2, C3, and C4. C4 times 0 would still always be 0. It's not contributing anything. So we say it's unnecessary. And we can go ahead and get rid of it. Just exclude it from the set. And then the other thing to take note of, this first one here, instead of using 3 plus 3x squared, so we can eliminate the multiple of 3. So instead of 3 plus 3x squared, we can just use 1 plus x squared because they cover the same thing and it's just multiplied by a constant. So 1 plus x squared, x plus x squared, and 1 minus 2x minus x squared. Now the next question, so the span of all of these vectors covers some portion of P2, right? Not necessarily every portion of P2. There could be polynomials that cannot be created out of the span of these. That's possible. But the question is, can these vectors create each other? Are there any dependencies among them? So we're going to check for linear dependencies. So when we check for LD, we put these coefficients into the columns of a matrix. So 1, 0, 1, 0, 1, 1, 1, negative 2, negative 1, 0, 0, 0. All right, so this is 1 plus 0x plus x squared, 0 plus x squared, 1 minus 2x minus x squared. And when checking for LD, you set those all equal to 0. If we perform EROs on this, it worked out pretty nice. The first and second rows basically eliminate the third. So we get 1, 0, 1, 0, 1, negative 2, and then a row of all zeros down at the bottom. So we get our pivots here, meaning this third vector is not necessary because we only have leading variables for the first and second columns. So the third one can be written as a combination of the first two, so it's unnecessary. So the range of T is the span of 1 plus x squared and x plus x squared. So if we were looking for a basis for the range, we wouldn't need the span. It would just be the vectors themselves. But as a note, the dimension of the range would just be the size of its basis, which would contain two vectors, two Li vectors that span. So just like we saw that the kernel was a subspace of V, the range is a subspace of W. So this one, we always kind of have to keep these straight. The kernel contains elements from V. The range contains elements from W. So because the range is going to be, so it's the span of T of V1, etc., up through T of Vn, where V1 through Vn is a basis for V. So, but each of these are not V1 through Vn, it's the transformations of V1 through Vn. So all of these are elements of W, not elements of V. Okay. And again, it doesn't necessarily cover all of W. It can, but it is covering a subset of W, which would be imbued with those same properties of the subspace. So the range of T is a subspace of W, of the output vector space. If we take a look once again at the matrix transformation, recall that we showed that the kernel of the transformation is the null space of A. It's the null space of the matrix. If we look at the range of T, that is the span of the transformation of each basis vector. So for X, it's going to be, I put these in columns because it multiplies, it multiplies like these ones with this one. It's a column vector. So we get 1 with zeros. We get 0, 1 with zeros. And then all zeros until we get to the 1 down at the bottom. So we transform each of these vectors. But when you transform them, each of these is just producing, when multiplied by A, it just produces a column of A. So each of these is just giving us in total the columns of A. Right? When you perform the matrix multiplication, that's what the transformation is. You transform by multiplying. This vector will transform into a column from A. And when you list all of them out together, it gives you all the columns of A. And the span of all the columns of A is the column space of A. So we saw that the kernel produced the null space of A, and now we see that the range produces the column space of A. Now that we have this information, we can kind of look at this a little bit differently when we're talking about like the dimension of these bases, because we have from chapter 4 the rank nullity theorem that said the rank of A plus the nullity of A equals n. We know that the column space, its dimension is the rank, and the null space, its dimension is the nullity. But the column space and the null space for the matrix transformation are just the range and the kernel. So the new theorem that we have here is that the dimension of the range of T plus the dimension of the kernel of T equals I shouldn't say n, because n is the dimension of V. That's the input vector space. Because remember, we go from Rn to Rm. Back up here. Dimension of the input vector space is n. So dimension of the range plus the dimension of the kernel equals the dimension of V. And this can be helpful when working with both. We can see how the size of one affects the size of the other, and we can see kind of how they interact in that way. And we'll be looking more in the upcoming sections as well at the implications of that. So let's take a look at this next example. So we have a transformation from M2 to P2 given with this relationship. Find a basis for the kernel of T. So this is the same transformation that we were working with a little bit ago. We found its range. Now we're going to go ahead and find its kernel. So we know that a matrix ABCD is in the kernel of T. Again, if and only if it transforms to 0. So if all of these become 0, so 3a plus c is 0, b minus 2c is 0, and 3a plus b minus c is 0. So if we go ahead and put all these equations in our matrix, that's going to be 3, 0, 1, 0, augmented with 0, 0, 1, negative 2, 0, 0, and 3, 1, negative 1, 0 with 0. And if we perform EROs on this, to simplify it down, put it in row echelon form, we get 1, 0, 1/3, 0. We get 0, 1, negative 2, 0. And we do also get an all 0 row at the bottom of this one. So in this case, we have two free variables. So D will be T, which is free. C will be R, which is also free. B minus 2R is 0, so B is 2R. And A plus 1/3 R is 0, so A is negative 1/3 R. So this tells us the general form of the kernel, right? Every 2 by 2 matrix that transforms to 0 has components that look like this. So the kernel of T is going to be the set we have here, negative 1/3 R, 2R, R, and T. So then to find the basis, as per usual, we bust out the variables. That would be R and T in this case, and just take the vectors from that linear combination. So we've got negative 1/3, 2, 1, 0, and 0, 0, 0, 1. That's our basis. So we can see here, of course, that the dimension of the kernel is 2. But if we look back at the previous iteration of this example, where we found the range, notice we saw that the dimension of the range was 2 as well. And if you look at our theorem here, dimension of range plus dimension of kernel should be equal to the dimension of V, where V is the input vector space. In this case, that's M2. Dimension of M2 is 2 squared, which is 4. So notice, so dimension of the range of T is 2. Dimension of the kernel of T is 2. Dimension of M2 of R is 4. And 2 plus 2 is 4. So this does satisfy that theorem. So their sizes are correct and appropriate. So, if you were getting a question that said, find the kernel of T, and then it just said, what is the dimension of the range of T? It didn't ask, what is the range? It just said, what is the dimension of the range? We could answer questions like that without actually having to find it. We would be able just to know the dimension of the input vector space and the dimension of one of them in order to find the other. And that works in both ways there. So we can, at this point, add a little bit extra onto our invertible matrix theorem. So we have a couple new conditions that are equivalent to a matrix being invertible, and that is for a transformation from Rn to Rm, the kernel of T is 0. So in other words, the only thing that transforms to 0 in the matrix transformation is 0. So only thing that translates to 0 is 0, or I shouldn't, not translates, transforms. Only thing that transforms to 0 is 0. That's what this is saying, okay, for a matrix transformation. If that's the case, then that matrix in the transformation is invertible. And then similarly, for a matrix transformation as above, if the range is all of Rn. Okay, so if the range covers all of Rn. Right. Speaking of the matrix transformation, got a little bit kind of pre-filled here. So given the matrix transformation, where A is an M by N matrix, how do we determine A? Well, we take the vectors, right, the basis vectors, 1 with 0, 0, 1, 0, zeros, all zeros up to 1. We take all of those column vectors, right, for x, and then transform them. Those transformations produce the columns of A, right? We saw that earlier when we looked at the column space. And so if you just take all those columns and just put them all next to each other, right, that forms the matrix A. So we can create the matrix A given some transformations. So for example, right here, we're going from R3 to R2 via T of 1, 0, 0 equals 3, negative 2. T of 0, 1, 0 is 0, 4. T of 0, 0, 1 is negative 1, negative 1. So our matrix in the matrix transformation, right, that would be the transformation of 1, 0, 0 with the transformation of 0, 1, 0 with the transformation of 0, 0, 1. So that's just going to be 3, negative 2, 0, 4, negative 1, negative 1. Right? And then just like as a note, to see that this does actually work properly as a matrix transformation, if you were to take A times X, so 3, 0, negative 1, negative 2, 4, negative 1, and then with 1, 0, 0, for example. So we would go row with column. That'd be 3, 0, 0. And then go row with column. So that's -2 with 0 and 0. And that, of course, was the vector that we saw in the transformation. Okay. And then it works the same way for the others as well. So because we were able to transform a basis, that gave us all of the columns for A, and then we can use A to transform anything. Okay, so not just these three. We could multiply it by any vector we wanted and get out the result for the transformation. So we can also get a little bit clever with this. So if we were going from R4 to R2, for example, so we know that T of 1 with zeros is this, with 1, 1, 0, 0 is this, 1, 1, 1, 0 is this, 1, 1, 1, 1, and 2 is 2, 2. If we want to create the matrix A for the matrix transformation, we need to transform a basis. This one, however, is not quite in that standard form of 1 with zeros, 0, 1, 0, 0, 0, 1, 0, and etc. We can create that basis out of these, however. So if we wanted to create 0, 1, 0, 0, using what we have, we could take 1, 1, 0, 0 and subtract off 1, 0, 0, 0. And what this gives us then is if we transform all of these, we know that transformation of this one is 5, 1, minus transformation of this one is 3, -2. So the transformation of 0, 1, 0, 0 is 2, 3. Okay, and then similarly, if we wanted transformation of 0, 0, 1, 0, we would take this one minus this one, right? And that would subtract off those two. So we get -1, 0 minus 5, 1. So -6, -1. And if we want the last one, we would take this one minus this one, right? That would leave us with only that last component. So we get 2, 2 minus -1, 0. So that is 3, 2. So our matrix A is going to be, so we start with this one. So 3, -2, 2, 3, -6, -1, and 3, 2. So that would be the matrix for the matrix transformation. For the others, so for like the range of T for this matrix transformation, that is the column space of A, right? So that's the span of all of the column vectors, 3, -2, 2, 3, -6, -1, and 3, 2. And all of these vectors, These vectors do span all of R2. So in this case, the range is the span of all these column vectors, which is all of R2. So you can create any vector in R2 using these four. And then for the kernel of T, that would be the null space of A. The null space for this one, it does not work out very nicely. So I'm just going to leave this as an exercise. If you want to try it, then you can go right ahead. It's not like the algebra is not inordinately complicated. It's just you get multiple free variables, you get some fractions involved in there and kind of long expressions. But it would still provide us with a set of vectors in terms of R and T, those free variables. So next up, let's take a look at another transformation here. Suppose that T is going from P1 to M32, and assume that is a linear transformation with T of 1 being this and T of 1 plus X being this. So instead of working with like, R2 and R3, kind of our typical ones that we're used to, we can work with alternatives. So we want to come up with the general transformation for T of A plus BX. So we know how to transform 1, and we know how to transform 1 plus X. Now we want to know, how do I transform, if I just had any general polynomial of degree 1 or less, how would I transform it? So I want to come up with a rule, right? A general rule for the transformation based off of the 2 that we know already. So T of 1, that's good. 1 is an element of the basis, but we really want T of X as well. That's the other element in the standard basis. So this is going to be T of 1 plus X minus 1. So let me rewrite that here. 1 plus X minus 1. Right? 1 minus 1 would cancel out, and we'd be left with X. So these are the same thing. And this is T of 1 plus X minus T of 1. And so basically we just take this matrix minus this one. So that's going to give us another 3 by 2. It's going to be 8, 1, negative 4, 1, negative 1, 4. So to transform a general polynomial, T of A plus BX, that's going to be T of A plus T of BX. So that's A times T of 1 plus B times T of X. So that's A times negative 2, 1, 3, 0, 1, negative 1 plus B times 6, 2, negative 1, 1. Oh no, sorry. It's the one that we found. 8, 1, negative 4, 1, negative 1, 4. And those, if you distribute in the A and the B, combine all of their terms, we're going to get negative 2A plus 8B, A plus B, 3A minus 4B, B, A minus B, and negative A plus 4B. So, given these two, we were able to come up with the transformations for the standard basis for T of 1 and for T of X, and use that to create the general rule for the transformation. which is this. So now given any polynomial of degree 1 or less, we can transform it into a 3 by 2 matrix using this rule that we have now just established. Right. And for this next example here, kind of going back to the idea of dimension a little bit, if the transformation is going from P6 to R5, so we're transforming from 6-degree polynomials or less to 5-dimensional ordered, right? Ordered 5 tuples, I guess, or quintuples. So if this is a linear transformation and we know that the dimension of the kernel is 2 already, what is the range of t? So the dimension of v, so that's the dimension of P6 of R, that's 7. And the dimension of the kernel of T, we are told, is 2. Then the dimension of the range plus dimension of the kernel equals dimension of V. So the dimension of the range is 5. But it didn't just ask us what is the dimension of the range. It asked what is the range. So now if we look at the size of the range, this means that a basis for the range has 5 vectors in it. And we're in R5 right now. So if the basis for the range has 5 vectors and the basis for R5 also has 5 vectors in it, the range and the output vector space are the same size. That means that the range covers all of it, okay? Or it spans all of it, if you will. So let me say that again. So since the range is the same size as the output vector space, their dimensions are the same, which means that the range spans all of R5. So notationally, we'll say the range of T is R5. Okay, and so again, they're same size, range spans all of R5. So we say that the range is R5 because it covers all of it. Right. And that brings us to the end of section 6.3. That is our introduction into the kernel and range of a linear transformation.